Hello everyone, welcome to this 15th lecture on topology. In this lecture we'll discuss about higher separation axioms. In the last lecture we discussed about lower separation axioms which covered T1 axiom and T2 axioms, and T2 axioms are known as Hausdorff spaces. In this lecture we'll discuss about regularity and normality, which comes under higher separation axiom. So here is the definition of regularity. A topological space X is said to be regular if for every closed set A and a point X outside A, there exist two open sets U and V, whereas this U contains X and V contains A, and these two open sets U and V are disjoint. If for every closed set A and a point outside it, there exist two disjoint open sets U and V which separates the point from that closed set, then only we say that the space is a regular space. Here we have the topological space X. This topological space X is said to be regular if for every closed set A and a point outside it. Here we have the point X which is outside A. If for every closed set A and for every point outside it, there exist two disjoint open sets U and V, whereas U contains the point X and V contains the closed set A, then only we say that the topological space X is regular. Here we have an example. Let X be the 3-point set ABC with the topology tau, which contains subsets as whole space X, empty set containing 2 points AB, set containing 2 point BC, and the singleton set B. Now we have to check whether this topological space is regular or not. Clearly, the open sets here these are the open sets. These are 5 open sets in this topological space, and we know that closed sets in a topological space are the complement of open sets. So now the closed sets in this topological spaces are complement of this open set AB, that is our singleton set C. This is closed. Complement of the open set BC. Here we have the singleton set A, which is a closed set. Similarly, complement of B is AC. So AC is a closed set in this topological space. And complement of this empty set is whole space. So whole space is also closed. Complement of this whole space is empty set. So empty set is a closed set here. So the only closed sets in this topological space are singleton set C, singleton set A, singleton set, set containing AC, whole space, and empty set. Now we have to check whether this topological space satisfies the condition of regularity or not. Let us take a closed set A containing 2 points AC, because here this set is a closed set. We have considered this closed set and a point outside it. Here we have the point B which is not in A. Does there exist two disjoint open sets which separate this closed set from this point B? That doesn't exist, because the only open set in this topological space which contains A is the whole space, but this whole space also contains the point B. So it cannot find two disjoint open sets in this topological space which separates A from the singleton point B. So this space is not regular. Here we have another example. Let X be the 3-point set ABC with topology tau containing whole space, empty set, a set containing 2 points AB, and the singleton set C. In this topological space, closed sets are empty set, whole space, singleton set C, and AB, because these are the complement of these open sets. Here we have 4 open sets, and complement of these 4 open sets are these, which are closed sets. Now we have to check whether this topological space satisfies the condition of regularity or not. Here, let us take any closed set. Let us take this closed set C and a point outside it. Let us consider the point A. If our closed set is this set C and a point outside it is A, then we can easily find out two disjoint open sets which separates them, because there is an open set C itself which contains the closed set C, and there is an open set AB which contains the point A. Similarly, for this closed set this closed set C and a point B outside it, we have the same open set A, B and C which separates this closed set from any point outside it, whether that is A or B, that can be separated from this closed set. Similarly, if we take the closed set AB, this AB is a closed set. If we take this closed set AB and the only point outside this closed set is C, they can also be separated by two disjoint open sets, because this AB and C separates this closed set AB from C. So this is a regular space. Here every closed set A and a point outside it are separated by two disjoint open sets. Now, what is a normal topological space? A topological space X is said to be normal if for every pair of disjoint closed sets A and B, there exist two open sets U and V, whereas U contains A, V contains B contains B, and U, V are disjoint. That means a topological space X is said to be normal if for every pair of disjoint closed sets AB, there exist two disjoint open sets U and V which separates those two closed sets. Here we have this topological space X, and we have here A and B. For every pair of disjoint closed sets A and B, if there exist two disjoint open sets U and V which separates them, then only we say that the space is normal. Here we have an example. Let X be the 3-point set ABC with the topology tau. Here we have, these are the open sets in this topology. We have 6 open sets here. Now the closed sets in this topological space are whole space, empty set, set containing BC, singleton set C, set containing AB, and singleton set B. Now here we can see that every pair of disjoint closed sets, there exist two disjoint open sets separating them, because here in these are the only closed sets here. So here you can see that B and C are disjoint closed sets. So if we consider these two disjoint closed sets B and C, for the closed set B we have here an open set AB which contains the closed set B, and for the closed set C we have an open set C which contains closed set C. So for this pair of disjoint closed set B and C, we have two disjoint open sets AB and C which separates them. And also we can see here that there is no other disjoint pair of closed sets. So here we can say that every pair of disjoint closed sets in this topological spaces can be separated by two disjoint open sets. So the space is normal. Let us consider this example. Again, X is a 3-point set ABC with the topology tau containing subsets as whole space X, empty set, singleton set A, set containing 2-point AB, singleton set C, and set containing 2 points AC. In this topological space, the closed sets are whole space, empty set, set containing BC, singleton set C, set containing AB, and singleton set B. These are the complement of these open sets. Let us check this topological space is whether normal or not, and this topological space is regular or not. Here we can see that every pair of disjoint closed sets, there exists two disjoint open sets separating them. Because in this topological space, here the pair of disjoint closed sets are here, B and C, which can be separated by two disjoint open sets here, A, B and C. So this is a normal topological space. Now let us check whether this is a regular topological space or not. Since here the closed set BC and a point outside it, A, cannot be separated by disjoint open set, this space is not regular. Here we can see that this set containing BC is a closed set here, and the only point outside it is the point A. And for this BC, closed set BC, we have the only open set here is whole space X, which contains this closed set BC. But this whole space X also contains the point A. So we cannot find two disjoint open sets containing BC and A respectively. So this space is not regular. Here we have one more example. Let X be ABC with topology X, empty set AB, BC and the singleton set B. Closed sets here are empty set, whole space, singleton set C, singleton set A and AC. Since here we have two disjoint closed sets C and A, let us check whether for this C and A there exists two disjoint open sets separating them or not. For this closed set C, we have a open set here BC which contains the closed set C. And for the closed set A, we have an open set here AB which contains this A. But these two open sets AB and BC are not disjoint. So we cannot find two disjoint open sets here in this topological space which separates the closed set C and closed set A. So this space is not normal. If we consider the real line with standard topology or usual topology, then that is both regular and normal, because in real line, standard topology or usual topology are generated from the basis consisting of all open intervals. So in real line, if we take any pair of two disjoint closed sets, we can easily separate them by two disjoint open sets. So the space is normal. Similarly, if we take a closed set in the real line, that means a closed interval and a point outside it, then we can find out easily two open intervals containing the closed interval and the point outside it. So the space is regular. So real line with usual topology is both regular and normal. Any infinite set with cofinite topology is neither regular nor normal. We have seen in our earlier lecture that uh, any infinite set with cofinite topology, if we consider any infinite set with cofinite topology, then there doesn't exist two disjoint open sets. So if we take two disjoint closed sets, we cannot find two disjoint open sets separating them. So the space cannot be normal. Similarly, if we take a closed set and a point outside it, then they cannot be separated by two disjoint open sets, because in the case of an infinite set with cofinite topology, there doesn't exist any disjoint open sets. So any infinite set with cofinite topology is neither regular nor normal. Similarly, any set with discrete topology is both normal and regular, because in case of discrete topology, every subset of that discrete topology is an open set. So if we take two disjoint closed sets, then we can very easily separate them by two disjoint open sets. Similarly, if we take a closed set and a point outside it, we can very easily separate them by two disjoint open sets. So any set with discrete topology is both normal and regular. We know that a normal space need not be regular. We have seen an example in the previous slides that a normal space need not be regular. But a T1 normal space is always regular. Let us prove this. Every T1 normal space is always regular. Let X be a T1 normal space. We have to prove that X is regular. To prove X is regular, let us take a arbitrarily closed set in X and a point outside it. Let A be a closed set in X and a point X which is outside A. Since X is a T1 space, the singleton set X is closed. We know that in a T1 space, every singleton set is closed. So this singleton set X is closed. Thus X is a closed set. And X is outside A and A is a closed set. So this singleton set X and A are two disjoint closed sets in X. And it is given that X is a T1 normal space. By normality of X, there exist two open sets U and V such that U contains the singleton set X and V contains the closed set A, whereas this U and V are disjoint by normality. Therefore, there exist two open sets U and V such that U contains X and V contains A, whereas U and V are disjoint. So the space is regular. Here we have a theorem, rather this is a characterization of the regularity. A topological space X is regular if and only for every X in X and for every open set U containing X, there exists an open set V such that X belongs to V, which is a subset of closure of V, and this closure of V is a subset of U. A topological space X is regular if and only for every X and for every open set U containing this X, there exists another open set V which contains that point X, and the closure of that open set V is a subset of the open set U. This is both ways. So this becomes a characterization of regularity. Let us prove this. Let X be a regular space and U be an open set containing a point X. Since U is open and X belongs to U, complement of U is closed. And this point X is outside X minus U. So here we have a closed set X minus U and a point X which is outside the closed set X minus U. Now by using the regularity condition, there exist two open sets V and W such that V contains the point X and W contains the closed set X minus U, whereas these two V and W are disjoint open sets. Because of regularity, we can find out two disjoint open sets V and W, which separates the closed set X minus U and a point X outside the closed set. From this, we have X belongs to V. If we take complement on both sides, then complement of W is a subset of U. Because X minus U is a subset of W, so X minus W is a subset of U. And here we have V and W are disjoint open sets. So V is a subset of complement of W, X minus W. So from this, we have X belongs to V and this B is a subset of x minus w. So B is a subset of x minus w, and this x minus w is a subset of u. We know that closure of V is the smallest closed set containing V. We know that closure of any set is the smallest closed set containing that set. So if we take closure of V, then the closure of V is the smallest closed set containing V. But here W is an open set and X minus W is a closed set. So X minus W is a closed set containing V. And closure of V is the smallest closed set containing V. So from here we can say that X minus W contains closure of V and closure of V contains V. So from here we can say that X belongs to V and V is a subset of closure of V, and closure of V is the smallest closed set containing V, and X minus W is a closed set which contains V. So this inclusion, we can write down this inclusion: closure of V is a subset of X minus W and X minus W is a subset of U. So we have X belongs to V is a subset of closure of V is a subset of U. This is one way of the proof of the theorem. Now to prove the converse, let for every X in X and for every open set U containing X, there exists an open set V such that X belongs to V is a subset of closure of V is a subset of U. Now we have to prove that X is regular. To prove X is regular, let us take a closed set A and a point X outside A. Since A is a closed set, complement of A is open. So here let us say U is equal to X minus A is an open set containing X, because X doesn't belongs to A, so X belongs to complement of A. And our complement of A is an open set and we took it as U. So U is an open set containing the point X. Now by the hypothesis, there exists an open set V such that X belongs to V and V is a subset of closure of V is a subset of U. So from here we have X belongs to V. X minus U is a subset of X minus closure of V, because here we have closure of V is a subset of U. Now taking complement on both sides, we have X minus U is a subset of X minus closure of V. So this second inclusion is here. And V and complement of closure of V, these are disjoint open sets. Because V is a subset of closure of V, V and complement of V are disjoint. Since V is an open set and closure of V is closed, so complement of closure of V is open. So X minus closure of V is an open set which is disjoint from the open set V. So here we have V is an open set which contains X, and X minus closure of V is another open set which contains A, because X minus closure of V contains X minus U and our U is X minus A. So X minus U is A. So A is a subset of X minus closure of V. So V and X minus closure of V are two disjoint open sets containing the point X and A respectively. So X is a regular topological space. So this completes the proof of the characterization of regularity. Now let us take a characterization of normality. A topological space X is normal if and only if for every closed set A and for every open set U, containing A, there exists an open set V such that A is a subset of V and B is a subset of closure of V and closure of V is subset of U. A topological space X is normal if and only for every closed set A and for every open set U containing this A, there exists another open set V such that A is a subset of V, is a subset of closure of V, is a subset of U. Let us prove this. Let X be a normal topological space. Let A be a closed set in X and U be an open set containing A. Since U is an open set, X minus U is closed and X minus U is disjoint from A because A is a closed set inside U. So complement of U is a closed set which is disjoint from the closed set A. Now we have two disjoint closed sets, X minus U and A are two disjoint closed sets in X. By normality of X, there exist two disjoint open sets V and W such that V contains A and W contains X minus U. Because X minus U and A are two disjoint closed sets and the space X is normal. So by normality of X, there exist two disjoint open sets V and W. V contains one of those closed sets A and W contains the other closed set, that is X minus U. And these V and W are disjoint. From here we have A is a subset of V, X minus U is a subset of W. So taking complement on both sides, X minus W is a subset of U. So X minus W is a subset of U. Here V and W are disjoint. So V is contained in X minus W. So we have A is a subset of V and V is a subset of X minus W and X minus W is a subset of U. Now here we can use the same logic that closure of V is the smallest closed set containing V and X minus W is a closed set containing V. Because W is open, so X minus W is closed. X minus W is a closed set containing V and closure of V is the smallest closed set containing V. So we can write down this inclusion. This is the smallest closed set containing V and this is closed set containing V. So closure of V is a subset of X minus W. So we have A is a subset of V, is a subset of closure of V, is a subset of U. This is one way of the proof. To prove the converse one, let for every closed set A and for every open set U containing A, there exists an open set V such that A is a subset of V, is a subset of closure of V, is a subset of U. Now we have to prove that X is normal. Now to prove X is normal, let us take two disjoint closed sets A and B in X. We have to show that there exist two disjoint open sets which separates A and B. Now A and B are two disjoint closed sets in X. So complement of this closed set B is a open set which contains A. Now let us take the complement of B as U. U is equal to X minus B. This is an open set which contains A because A and B are two disjoint closed set. So complement of B is an open set containing the closed set A. Now by the hypothesis, there exists an open set B such that A is a subset of V, is a subset of closure of B, is a subset of U. That means A is a subset of B. Since closure of B is a subset of U, taking complement on both sides, complement of U is a subset of complement of closure of B. So X minus U is a subset of X minus closure of B. Since B and closure of B is a subset of closure of B, B and complement of closure of B are disjoint. So B intersection Complement of closure of B is empty. Now closure of B is a closed set, so X minus closure of B is an open set. So here we have two disjoint open sets, B and X minus closure of B. These are two disjoint open sets. And B contains A, and X minus closure of B contains X minus U. And our U is X minus B. So X minus U is our B. So this open set X minus closure of B contains the other closed set B. So here we have two disjoint open sets B and complement of closure of B are two disjoint open sets containing A and B respectively. So the space is normal. So this completes the characterization of normality. In the next lecture, we'll study some other result of normality and regularity.